Today I'll be presenting the quantitative analysis of flow characteristics and contaminant dispersion in urban canopies. The motivation of this research was to see how passive contaminants in the urban environment disperses, for example, contaminant within a crowded city. The new techniques that we use, such as the MRI measurement techniques, offered high-resolution 3D measurements of the velocity throughout the canopy. This gave us a full field data for the simplified building array. The objective of this research is to find out how the mean flow structure is related to the scalar dispersion of the contaminant, and to see whether the turbulent or geometrical dispersion is dominant within the canopy when the contaminant disperses. We use the MR imaging of turbulent water flows for both the velocity and the contaminant. For the MR velocity measurements, we could get a 3D three direction mean velocity vectors with the isotropic resolution of 0.06h. For the contaminant dispersion, we use the neutrally buoyant copper sulfate solution injected through the porous plug within the water channel, as you can see above, with 2 levels of injected concentrations to resolve mixed regions. This imaging technique involves putting a water channel through the MRI machine to get the 3D measurements of the velocity as well as the contaminants. This is the building canopy that we used, which has 48 short buildings, which are cubical, and one central tall building. We used 2 orientations, the 0 degree, in which the direction of the bulk flow is aligned with the direction of the boulevards, and the 45 degrees, in which the streets are skewed at a 45 angle with respect to the direction of the bulk flow. The tall building is indicated with the red arrow. This is a top-down view of the same canopy with the red squares indicating the location of the tall buildings. The bulk flow travels in the x direction for our research, and the center of the coordinate is defined as the center of the tall building at the level of the floor. H is a length scale that we'll be using repeatedly, and this refers to the height of the cubical short building. The tall building has a height of 3h. We'll now look into the flow characteristics. This is the iso contours of the streamwise velocity, the x velocity, at y equals 0.49h, which is approximately the mid-height of the short building. The streamlines are also released at the same height. In the 0 degree case, we can see how the incoming flow is moving relatively smoothly down the boulevards in between the spaces between the buildings. In the 45 degree case, however, the flow is a lot more varied. We can see vortices occurring behind the buildings in the first row of the short buildings, and we can also see how the flow crosses over the short buildings that come after the first row. The wake incorporates almost none of the incoming flow according to the streamlines. We'll now look into the vertical velocity. The most striking characteristic when we look into the vertical velocity is a chimney effect that happens right behind the tall building. The flow which comes in goes around the tall building, accelerates, and then it moves upwards into the region of the lower pressure as indicated with the red arrow. Then this streamlines then is propagated into the rest of the canopy while in the direction of the bulk flow. This is also seen in the 45 degree case, where in this case, we can see a lot of vorticity behind the tall building, but as in the 0 degree case, the streamlines then propagates in the direction of the bulk flow and at an approximately same direction of the bulk flow. This is the separation bubbles for the 0 and the 45 degree case. In the 0 degree case, we can see that the separation bubbles are relatively short compared to the short buildings. It's around the mid-height. It comes around to the mid-height of the short buildings. In the 45 degree case, however, the separation bubble spans the entire height of the individual short buildings. So the volume of the separation bubble is a lot higher in the 45 degree case, even considering that the buildings have a higher cross-sectional area in relation to the bulk flow. We'll now look into the contaminant part. Here is the same top-down view of the canopy, the red indicating the tall building, while the newly added gray square shows where the injection point of the copper sulfate that we used. Note how in the 45-degree case, the injection point is to the positive z side of the tall building. This is a 10% contaminant isosurface, which gives us an idea of how the contaminant initially disperses. As we can see in both the 0 and the 45-degree case, the contaminant disperses by climbing up the tall building, and it almost seems to fill out this space behind the tall building. It almost seems to fill out the separation bubble. In the 45-degree case, we can see that the height of the isosurface is lower compared to 0 since it has a bigger cross-sectional area. But the most important thing in the 45-degree case isosurface is the area indicated with the red arrow of how the contaminant disperses not only behind the tall building, as in the 0-degree case, but also down the boulevards in the positive z direction. This happens at a considerably lower height with respect to the rest of the contaminant isosurface. We can look at this in more detail in this slide, the 3% contaminant isosurface. The blue indicates the isosurface at the level above H, so above the level of the short buildings, while red is the isosurface beneath the height of the short building. So anything up to 0 to H is in red, and H to 3H is in blue, and H and above is in blue. As before, in the 0-degree case, the contaminant isosurface, the contaminant plume, is contained almost perfectly within the wake of the tall building. In the 45-degree case, the blue isosurface seems to show this characteristics of being contained within the wake. However, the red isosurface, the isosurface from 0 to H, shows how the geometrical dispersion really dominates the dispersion at this height. As the contaminant tries to move down the boulevards in the positive z direction. We could attribute this to the fact that in the 0-degree case, the flow down the boulevards is a lot faster since there's no obstructions and it is perfectly aligned. But in the 45-degree case, it is skewed, therefore more obstructions, therefore the flow becomes slower, and it's easier for the contaminant to disperse geometrically because there is no bulk flow or high-speed flow that is wiping it out. We can see this also in the concentration contours at different levels. This is for y equals 0.49. And as we can see, in the 0-degree case, the concentration is a lot more concentrated in the area right behind the tall building. But in the 45-degree case, it's a lot more watered down since it starts moving down the boulevards and disperses through a larger area. At y equals 0.98, we can still see in the 45-degree case the effect of the geometrical dispersion, but when we hit y equals 1.96h, which is around 2h, so considerably above the height of the short buildings, the concentration characteristics are almost similar. It shows this plume, which is contained within the wake of the tall building. To summarize this research, we can firstly acknowledge how this MRI measuring technique allowed us to have full 3D data sets for the velocity and the concentration, which allows us to draw a spatial relation between these two. We can also see that there is a strong vertical velocity directly behind the tall buildings, which transports the contaminant into the mainstream. So as before, our injection point was at the floor. However, this chimney effect allows this concentration to move upwards and then propagate in the direction of the bulk flow. The turbulence of the building wake rapidly disperses the upper stem of the plume, and the dispersion within the canopy is highly sensitive to the flow alignment, especially at lower heights. The geometrical dispersion dominates in the canopy for the misaligned flow, which we could see in the 45-degree case. This would be the entirety of my presentation, and thank you.